then we continue with the next speaker, Mike McWilliam from DTU.
Yeah.
This time, which theory do we learn?
Elastic actually, I'm just going to tell you what people told me this time.
Okay.
Yes, so my name is Mike McWilliam. I'm going to have to be a bit fast because I have a flight to catch, so I apologize, but maybe you can record me and play it back in slow speed. Yes, so what I'm presenting here is a collaboration with a bunch of people here. The history of this collaboration was Workpackage 2 and IEA Task, where we're working on sort of reference models and metrics for models and things of this nature. Me and Jason Yonkman behind the scenes started talking about, working towards sort of having some benchmark cases. And then in the IEA, Airborne Wind Energy Conference last year in Milano, some people also wanted to talk about maybe standardizing how different disciplinary models kind of interact together. And so this is sort of similar to the presentation of Dylan about trying to kind of enable collaboration and getting different people's models together, working together, and sort of having some common standards that we can sort of measure these models up against to sort of make sure we're sort of confident in our models. So this is sort of the thing that we're trying to achieve in Workpackage 2, and among other things, I'm not going to say that that's everything, and sort of to help us sort of prioritize our work. So I'm coming from conventional wind. I don't know everything about airborne, and so we just decided to send out a survey to sort of the community to kind of get people's opinions on different topics. And yeah, and so then basically this presentation is the results of those surveys. And I would like to also thank Stefan Toms and Christian Petrick. They were very important people to help distribute the survey. And for everyone in this room who filled out the survey, I also want to thank all of you. So yeah, so thank you very much. And I think I just talked about everything that was on this slide. This was basically like our long-term, what we're trying to achieve in Workpackage 2. So we can get into the survey results, and probably the first thing we want to talk about is we had a roughly 20 responses. So we didn't do as well as, I don't see her in the audience, but Helena, so she did the, but yeah, okay, yeah. So we didn't do quite as well as Helena, but I'm actually quite happy with this nonetheless. So we have, 40% were airborne developers and 13% were academics. And it was nice to see that we had sort of a consultant and a financial analyst in the mix. So we were trying to, so we actually had some people that I thought would be rare, but nice to see it. And then we also wanted to see like what technology these peoples were interested in. So vast majority are sort of looking at these kind of pumping hard wing kites, and then a larger, next biggest group are these sort of flight generation hard wing, and then we have these pumping soft wing. There's actually a surprising number of rotary transmission, couple lighter than air, and then we allowed people just to fill in their own, and so we had also a category for people who are just interested in airborne at large. So that's probably the financial analyst. Anyways. Yeah, and then we also asked about what models people already use, and unlike conventional wind energy, in conventional wind energy there's basically kind of 3 big models that people use for wind turbines, but it's quite diverse, and most people use home-built models, and MATLAB comes up a lot. There's some C++, some people mention Python, so there's a wide variety of different models that people are using. There isn't really a convergence towards one. So it's wild, wild west in that regard. Which question is this? Okay, so then we also asked people what are they using their models for, and quite a lot of different things actually. So it's very, so developing their 2D controllers, think one of them was, this was sort of control regulation, estimating power, assessing loads, preliminary estimates for costs, preliminary design, detailed design to a lesser extent, certification to a lesser extent. There's somebody who did the survey who doesn't use models or doesn't develop models, but thank you for filling out the survey. But anyway, so people are using the models for a lot of different purposes. There wasn't just one purpose for using the model. So it makes our job as trying to figure out benchmarks a little bit harder because we need a benchmark for everything now. Yeah, and then I also was kind of considering, like, you know, a lot of people use models just for doing simulation, but you can also use models coupled with other algorithms to sort of optimization, uncertainty quantification, things of that sort. So we wanted to sort of figure out if people are doing sort of meta-analysis methods. So no surprise, numerical optimization, we always want to make everything better. But then there are people who are doing a little bit of uncertainty quantification, reliability, and some machine learning. So there's that. And now we started to try to ask questions more about kind of what types of models people are using. So in wind energy, we have this like hierarchy of different fidelities, and so we asked people, like, what fidelity do you use? So low, medium, and high, essentially. So most people consider their tool set to be medium fidelity. Some people low, and some people high fidelity. But then when you look into these sort of extra comments, there's a lot of people who are using a full range of fidelity. So, you know, maybe low fidelity for preliminary design, and then high fidelity for detailed design. So that wasn't surprising. We also considered what type, because as we know, machine learning and statistical methods and big data, right, we can actually develop models that are not physics-based anymore, just data-driven models. So we wanted to see, is the airborne wind energy community developing these types of models? And vast majority of the models are actually pure physics-based, or physics-based with maybe some data-driven components to it. So we have some mostly physicists in the room, and the data scientists haven't taken over yet. So that's where it is for the models. But then I also wanted to ask about to what extent people thought that their models were multidisciplinary or monodisciplinary. So in the early days of conventional wind energy, you would find like a separate bend model or a separate structure model. So I think with airborne, it's more difficult to kind of separate out the disciplines and get realistic results. And that's kind of what we see here. So most people are claiming that their model chain includes a lot of multidisciplinary aspects. So this is not a surprise to me. I think it would be difficult to get good results otherwise. And then the next set of questions we asked, it's a lot of data to sort of show in graphical form, was we were sort of asking how important people thought certain disciplines were. We had a long list of disciplines, and people could score their importance from 1 to 5. And so instead of showing like a ton of bar charts, I think we just decided to show what were the disciplines, the 5 most important disciplines according to the average, and then the 5 least important according to the average. And then you can kind of see to what extent did people agree with each other. So for example, most people agreed that the controller was important. And that's the primary mechanism that you guys stay up in the air, so that was not surprising to me. And so what people think are the most important things is basically the flight mechanics, staying up in the air, making sure everything stays together and is controlled. So the primary function of the airborne device, that's what everyone thinks is important. And then some of these additional things were less important. Yeah. And I think with the wind energy, it was a sort of a similar development. People focused a lot on rotor aerodynamics at the beginning, but now that in wind energy, we have a lot of money building huge projects, and a lot of the costs actually come out of this. We've sort of seen this shift in the importance. The next thing we asked is how confident people are in the following models. So we're trying to get a sense of like where we would need to prioritize our work for like developing benchmarking. And so it's similar sort of set of models. So that areas where people think are important, and everyone's doing home-built models, so the important areas is where they're putting their most work in, and so they've probably done a good job of trying to reduce the uncertainty in these areas that are important. And then I took the idea of taking the importance data and the confidence data and sort of doing a dot product of this data, and then using this dot product we could actually figure out like what are the disciplines that are both important and maybe we don't have a lot of confidence in. Could we kind of identify a discipline where we need to maybe focus our validation effort? And if you look at the data here, we see a lot of the same things in the bottom 5 and the top 5. So the dot product, surprisingly, actually came up to including a lot of the most important disciplines, having the main, being near the top of this kind of dot product metric. But you can see from the worst dot product value to the best dot product, it's not a very big spread. So it's clear to me, like economics being, a lot of people think it's important, that's obvious, but there's a lot of uncertainty. I would say that's a function of the maturity. We're still developing, and what the final product is going to cost, we don't know. But I think if we're going to do benchmarking, wing aerodynamics, model coupling, this is something that if we want to bring models together, dynamics and tether models. I'm going to try to hurry up, maybe, I don't know what time it is. I forget what this is. Ah, yeah. And then we asked people, sorry? Oh shoot, I gotta run. Yeah, so then we asked people what they thought was most important about their models: reliability, energy production, cost, and safety. Pretty obvious. And then conclusions and goodbye.